Okay, with that, let's move on to the training. We're going to begin with the training of the discriminator. It's a type of neural network. More specifically, it's a convolutional neural network, or CNN for short. And I won't dive into the specifics of CNNs in this lecture, but for now, in this context, just think of it as a network that automatically learns to recognize key patterns and features within an image. The discriminator's job is to act like a critic and predict if an image it sees is real or fake. In our case, the discriminator is trained on real dog images from the training dataset that we have prepared. Now it is going to learn what a genuine dog looks like. As part of the learning, the discriminator passes the images through its convolutional neural network for a feature extraction. The CNN applies a series of filters to the images through multiple layers, helping the discriminator recognize things like textures and the shapes and the patterns. For example, some of the features extracted might include the shape of the dog, the texture of the fur, and the edges around the dog, and it's all happening automatically as the images flow through the network. Now we can assume that the discriminator has seen a lot of dog images, let's say 5,000, and it's going to output a probability, a number between 0 and 1 that represent how likely the discriminator thinks the image of that dog is real or fake. In this case, because the discriminator has already been trained to recognize real dog images, it predicts a value of 0.7. Now, a value close to 1 means that the model believes that the image is likely real. A value close to 0 suggests that the discriminator thinks that the image is likely fake. Now, you might wonder, how can the model even know what's real or fake in the first place? Well, during the training process, the algorithm labels real images with a 1. And this makes the discriminator's training kind of like supervised learning, because it's learning to tell the difference between real and fake images using these labels. After the prediction, the algorithm steps in and calculates the error using something called a loss function. Now, the loss function essentially measures how far the prediction from the discriminator is from the correct label. A value of 0.7 isn't too far from 1, so the loss is minimal in this case. Note that this is not simply a matter of subtracting 1 minus 0.7. The loss function uses a more complex calculation to measure the error. Next, the algorithm kicks in with backpropagation. Now, backpropagation is a feedback mechanism where the algorithm figures out how much each parameter in the discriminator contributed to the error. Once those contributions are determined, the parameters of the CNN are adjusted accordingly to reduce the error. Eventually, the discriminator becomes better, and over time, as more parameters are fine-tuned, the discriminator consistently improves its ability to distinguish real images. So now we have trained the discriminator with real images from our training dataset. Now we can bring in our adversary to continue the training of the discriminator. The generator. It's also a convolutional neural network, and its job is to generate images that fool the discriminator. When the generator is used for the first time, and in this case it has never been trained, it starts with a completely random input, what we call a random noise vector. If you're not familiar with the concept of vectors, that's okay. Just think of them as arrays of numbers. In this case, they are random, and typically the more values you find in a vector, the more complex things are. So in this case, the more values you see in this vector, the more complex the images are going to be. Now, because our generator is only getting started, this is the image that it creates. It's not very convincing, but that's a start. The discriminator then steps in to evaluate the image and decide whether it looks real or fake. It uses its convolutional neural network to process the fake image, and it analyzes patterns, edges, texture, and other important features to better understand it. Notice that this time the algorithm assigned a label of 0. And this happens because the algorithm knows that the image comes from the generator, meaning it is fake by definition. Now let's see how well the discriminator's prediction aligns with the label and what that means for the overall performance. As expected, the discriminator easily spotted that the image is fake because it looks like nothing like a dog. The prediction score is only 0.1. The algorithm calculates the error or the loss function based on the difference between the discriminator's prediction and the actual label, and since the fake image was easily detected, the loss is minimal. Backpropagation still occurs with minimal changes to the discriminator's internal parameters since the loss is already low. Now that the discriminator has learned how to discriminate real images, we need to train the generator to produce really convincing fake images.